Okay, hello and welcome to another session of coding on PICO-8. And now you might be looking at the PICO-8 screen and wondering what the heck's going on there. Did it crash or something? No, it didn't. And also, if you've ever downloaded a demo and seen something like that in the sprite sheet, you may also have wondered what's going on there. What is going on there is that it's compressed data stored in several places on the card, which can be used to store compressed data, which includes the sprite map, the map sheet that you normally use if you do some kind of tile-based game, and the area used for the soundtrack. All of these are accessible. All of these can be saved onto the card, and you can use them as data storage. And the total amount of bytes you can store in this way is 17,125 bytes. And I'm gonna be showing now how to do some of those tricks. I'm gonna show you how to do a simple RLE compression function. It's definitely not the most efficient compression function there is, but it's simple to code, it's simple to grasp if you've never coded any compression functions, and it's useful because it takes fairly few tokens to unpack, which is important if you're doing a big program in PICO-8. It's easy to run out of tokens, and you can combine it with some other compression algorithm, because whatever you get out of the RLE compression root function will still probably compress pretty well using something else like Hoffman coding, for example. But yeah, let's start. And I have a example picture here. This is hi Mantratronic, welcome to the stream. And here's something from revision last week, and I hope you all watched revision. It was awesome. It was definitely, well, the word historic is pretty overused, but it was definitely a historic demo party. And if you didn't watch it, if you didn't take part in it, you should check it on YouTube, on Twitch VOD, wherever it's available, because there were some amazing demos and other demos in releases there. And this is not one of the amazing releases, but it was my entry in the Paint Over Fast Graphics competition. So it looks like that, and the code looks like this. Now I get to show you. I think most people probably know this already, but in case you're wondering what the palette commands here mean, there's an unofficial secondary palette in PICO-8, which makes another 16 colors, and it's not officially documented, but Zep is okay with everyone knowing about it. You can't do any like scanline tricks with it like you could on an actual 8-bit platform. It's just strictly you can change the palette once per frame, so it's still a total of 16 colors on the screen simultaneously, but it allows for smooth dithering, smooth shading, and 3D systems and stuff like that, so it's very useful to know. And also, if you use this poke, then it means that the palette you set in the program the palette stays, so you can use it in the built-in sprite editor. But yeah, let's start making that RLE compression function. Now, The way RLE works is basically it's an acronym for run length encoding. So basically it just and it's useful for low color, low resolution graphics. So it starts reading the data you want to pack, like for example this data here, and it sees that there are 4 A's in a row. So it would store that as 7A. Now this is very efficient when you have long runs like this. It's not terribly efficient if you have lots of noise or dithering like here, and if your data consists of mostly things like that, the compressed result may even be larger than the original. But I've tried RLE on this picture before, and it compresses not amazingly well, but pretty okay. So let's start. So let's run init function here. Let's do all the compressing in there so it only does it once. So, and we're gonna do that mem copy that copies the contents of the screen, of the sprite map to the screen. We're gonna put it in the init. And now let's start creating our loop. So this picture is 72 pixels high and 73 pixels wide, and no, actually it was 72 and 128 pixels wide. So we're gonna do nested for loops for that. And for every pixel we need to do value equals pget x comma y. So it reads the, or we could read it from the sample, the sprite map. So like this. So that does it. That reads the pixel from the sprite map. I could show you how it demonstrate. Like if we now do pset x, y, and value, and you flip here, then we will actually see it drawing the picture. Oh yeah, and I need to clear the screen, obviously. Yeah, so now you see it drawing it 1 pixel at a time. Yeah. And now that we have the value, we can compare it against old value. Now let's define a string called, an integer called old value, and let's have it be something that the sget result can never be, like 17. And let's define run length as 0, because we have not, our run starts at 0 length. So now it gets the value of the pixel, then it checks if value equals old value, then it just increases the run length, and at this point it won't do anything else. We'll add something more to this route later. Now, if value is not equal to old value, then we'll change the checking value to value. So now we're looking for pixels of this color, and then it checks if run length is greater than 0, then and we're gonna want to write this to this screen. So let's do write x is 0 and write y is 0. So we can actually draw this into the screen memory. So if run length is greater than 0, that means we have a length there. So we will set write x, write y with the run length, and write x plus 1 with the old value, which of course we're gonna have to change after this thing is done. Now, then it changes the old value and resets the run length sets it to 1, because the new run is going to, it's already seen the first pixel of the next run. So the run length is going to be 1 at this point. Also, we can only store numbers up to 16 here. So we'll actually want to make sure that the run length is smaller than 16. And of course, there's no color 16. We're going to want to encode values from 1 to 16 to 0 to 15. So the pixel is actually going to be pixel color is actually going to be run length -1. And at this point, write x should be incremented by 2, and if write x is now greater than 127, then write x should be 0 and write y should be incremented by 1. Now, let's see if we've made any obvious mistakes here. If value, double equals for comparing a value, and I'm missing a then, and I'm missing a then. Oh, it seems to have written something there. So this is now, if I've done everything correctly, this is now a compressed version of our picture. So let's make a function of this, call it RLE encode. Now, let's check if we did this correctly. So let's do another function. and call it RLE decode. So oh yeah, and let's now at the end of RLE encode, let's overwrite the old sprite map with our compressed picture. Now, let's start depacking it. So again, read X is 0, read Y is 0. Let's put an underscore there so it won't look like ready. And now, while get read X read Y is something other than 0, so this will stop running as soon as it encounters a pixel on the sprite map that's black. That means that there's gonna be zero run length, then it stops. Oh yeah. So it's gonna stop running at that point. So run length is sget read X, read Y. And value is sget read X plus 1, read Y. And of course we're gonna need to write this somewhere, so let's also define write X and write 0. And now let's do a loop. For I is 1 to run length, be set write X, write Y value, and increment write X by 1, and if write X is greater than 127, we reach the end of the scan line. Then start a new scan line, write X equals 0, write Y is incremented by 1. Okay. Now, RLE encode and RLE decode. Those are now both called in our init function. And yes, and of course we need to, at the end of this loop, we also need to increment the read values. Now, let's see if I did everything right. And I'm missing a do here. And interesting. I did mess something up, but what did I mess up? Okay, it's just writing those pixels there. Okay. Interesting. Okay, now we're gonna have to debug, because it doesn't seem to be writing all that much. So print let's get 2 0. By chance, are you writing and reading the same memory locations? I'm not doing that here, I think, because I have now copied the picture to the sprite map. So I should be reading the sprite map and writing it in the screen, I think. So let's see now. So the value of the pixel 2.0 on the sprite map should be non-zero. So there's something amiss here. Something is amiss and I am not sure what. But a piece that could go to screen. Yeah. So this is embarrassing. I don't know what the issue is here. Let's do. Let's debug a bit. So let's do a black rectangle at somewhere near the bottom of the screen, and let's use that to which was the correct order to do this again? Was it 202? Was it like that? Oh yeah, and I need to change the color obviously, because now it's just writing black on black. Oh yeah, and I need to put it on the near to the bottom, so oh yeah. So, okay, now let's see if the right X is being incremented. Okay, it stops being incremented. Let's check if it goes through this whole thing or if it just hangs. So it does go through the loop, but it decides at some point to stop. So let's debug this. So the point at which it stops running is X, Y, I mean 10 and 0. So is that black, really? Yes, because now I'm using the black to signify that the run is over, but I'm also using black to signify a run length of 1. This is the issue here. So we need to do this instead. Now it should work, I think. Yes. So yeah, now we have a working run length encoder and a working run length decoder. And let's see approximately how much smaller the encoded picture is. So compared, the size is around that, so it's not terribly efficient, but like I said, this data is is easy to compress further with something else. My demo toolchain uses Huffman coding. I'm not going to show you how to do Huffman coding because well, better teachers than me have made videos about it already, and you need to use like binary trees and recursive functions, things that aren't terribly complicated, but they're kind of beyond my abilities as a teacher. This is an awesome song, by the way. This was one of the music competitions at Revision. So now we'll get to show you how to copy this data to another card. So I've started an empty card of PICO-8. Would switching X and Y for the encoder produce smaller ROE results? Well, possibly yes. It depends on the source picture, and of course the problem with this particular version of the encoder is also that it needs to have an empty pixel as a signifier for the run to end. Also, our decoder now specifically reads data from the sprite map. It's possible to make a decoder that would read the data from any arbitrary memory location, but like I've done in my demo systems, but then you wouldn't be able to use sget. So this is then you basically, because every like the memory is an 8-bit memory, and all the pixels are 16 colors, so there are 4 bits. So every location in the memory stores 2 pixels. So basically, you could, for example, read the pixels with a peek command, and then split that 8-bit value to the most significant bits and the least significant bits, and do it like that if you need to use memory outside the sprite map. But yeah, now let's copy this to our empty cartridge. And so now we're gonna need to copy this encoded picture to the sprite memory. So after that we can use CStore. CStore is a very handy command. See if I've written the syntax down here. So yes, what CStore does is it takes a len amount of data from the memory of the card that's running currently, and stores it into a card data address defined by this dest adder. And like I said, the card data memory space is only about 17,000 bytes, so it needs to end before 0x4300. Also, if you use the entire card data, it also overwrites the soundtrack. So you all need to compress the soundtrack as well, and then use some function to write that into the correct memory locations. But yeah, let's show. So the sprite map starts at 0. The memory. Actually, I'm gonna try something that I haven't tried. Let's see if we can copy the screen directly. I don't know if this source can be anything from the memory. Let's try this. But if it doesn't work, then we can just copy it from the sprite map. So now we're copying from memory location 6000 in hexadecimal, we're copying it to card data address 0, and we're copying 8192 bytes, so that's the entire sprite map, and we're going to be copying it to a file called PICO-8, which date of today, P8. Now, let's see if this worked. And you saw a symbol in the top left corner. It means that it at least tried to save something. Now, let's see. And interesting. Did I write that? No, I did not write that correctly. So, another try. So now it should have... Is the issue actually that... Oh, and there's one. Yeah, and I also yeah. Thanks, Truck. I missed a 0 in my data and also had one hyphen too many. So now do we have the correct name file? Still no. Do I actually have a file of that name now? I do. So why did it not update it here? Let's see what it wrote here. It wrote nothing here. So yes, I guess the issue is that it in fact cannot copy directly from the screen. That's no problem. We'll do it this way instead. So we copy the sprite map to the sprite map. This should work. Now. Yes, now the file has been modified by another program. And we have the uncompressed picture here. Of course, we don't want to do that. We want to copy the compressed picture instead, because we want to store it as compressed. So now we should have a jumble of pixels here. Yes, we do. And now let's copy our hourly decode function to this card here. And no, we don't actually need... Oh, well, let's keep the encode here so I can upload that function to GitHub as well when I'm done. So we should do it. And hourly decode. And function update 60. Function draw, and let's see if it works. And again, in a draw loop, we'll be copying the contents of this sprite map to the screen, and we'll also gonna want to have this palette changing function commands here, so it will actually look nice and pretty. So, is everything okay? Yes, everything is okay. And yeah, so just to illustrate, also have an example of this card with the picture where I also have the, well, I've also included my other compression algorithms I mean my other, so basically Huffman. So just illustrate just pure RLE in this version. It's about that much smaller. Now let's use the Huffman coding instead. So it's that size. But of course we can combine these two. We can first do a run of RLE compression and then a run of Huffman compression, and we're going to be able to squeeze this into a smaller size still. Not a lot smaller, but smaller anyway. Actually, how much smaller was it? Yeah, it's definitely smaller. And the way my asset handler works is basically this is the version of this is the asset handler, the asset packer system that I'm using. These are the data, some of the data I've used in Pudoresurnasation, my demo for instance, and this is all the data in uncompressed form as strings, and you can't fit all. I couldn't fit all of the data on one card in as strings. So this basically what it does is it goes through these. It does several configurations where it compares which is the best, the like RLE or Huffman or RLE through Huffman, or in some cases actually the best is the original uncompressed version, and then it saves that into another card, another file that contains all the compressed data up to that point, and then it loads Packer-2, which contains more data. It loads Packer metadata P8L and compresses more data and adds that there. And finally, it gets to a Packer finalize, which sorts all the data, writes it into memory, writes that into the card that we're working on, and also creates a bit of code for the loader. So this is instructions for my asset loader. So this thing here is basically the locations of each asset in the card memory, and also the what functions it's supposed to use to unpack that data. And this small bit here is just a little bit of data that couldn't fit in the card data. And what it does is data is going to be a string into which we dump the whole content of the card data plus this string, and asset list is going to be the list of it's going to be kind of like a header read by unpack asset, which is a recursive function that I have that basically defines all these variables, all these strings which we can then unpack to usable assets. If this looks ugly, then that's because it is, because this is okay. Well, welcome to token optimization world. This is the reason this is a recursive function is so that I can do it all with just one function call, because I wanted to avoid having these equal signs, because every equal sign is one more token. So yeah, token optimized PICO-8 Lua is weird and unreadable, but that's how it is. So I'm just gonna show what it looks like when it goes through all the data. But can you compress code itself and decompress and run it? No, you can only write into the you can't write into the stack. You can't write into the area where the code resides. You can't do anything like self-modifying code in PICO-8, as far as I know. There might be a hidden way to do that, and Zep might be chuckling to himself right now, wondering when someone finds that, but there is no official way to do that, and there is no known way to do that. And I actually don't think there is a way to do that, because it would make it fairly trivial to bypass all the token limitations. So probably there is no way to do that. But not a stupid question. I'm like that. That's of course something that I tried to figure out myself, but there was no way to. There was no trick to do that I could think of. So this is now I've now loaded the packer. So let's run it. So now you can see that it compares different configurations for each asset. It's gonna say failure a couple of times, but it still works. That just means that for one reason or another, the compression function couldn't. That particular compression function couldn't handle that particular bit of data. So, as you can see, in most cases, the best result is something that has Huffman in it. Usually pure Huffman, or that RLE into Huffman. And you can also see that we have a very small asset here of a length of 64 bytes, where the winner is no compression. That means that every compressed version of that particular asset has actually been larger than 64 bits. So the system then stores it uncompressed. Hi Ryder, how you doing? By the way, you did awesomely in the shader showdown, by the way, as did everyone else. And so yeah, that was. Yeah, you should watch the shader showdown as well if you haven't seen it. So now now I've basically shown the asset handling system, so we still have some time to do some silliness with visuals. So let's go back to here. Okay, is everything still okay here? Yeah, it is. Now, so to start off, let's define again a frame counter and increment it every update 60. Now, let's define some coordinates. These coordinates are going to be 3, x is going to be 3, y is going to be 1, and z is also going to be 1. Now, let's make another coordinate. The same coordinate except y is -1. Now, let's define a theta for rotation. So let's say something like theta is f times 0.01. Now, I still haven't been able to memorize the rotation matrices, so let's cheat a bit and copy this here. So let's rotate both of these around the x-axis. So y is y times cosine theta minus z times sine theta, and z is y times sine theta plus z times cosine theta. And let's do the same to the other. And nothing happens to x yet. And now let's also translate it so it's not gonna. So now it's rotating around the camera, so let's move both of the z values a bit away from the camera like that. And let's copy our point flattening functions here. So now point equals flatten point x1, y1, z1, and let's add a CLS here, and b set point 1, point 2, 15. So now it draws that point as, I think it's pink or something, and let's do that to the other coordinates. Now let's see if I did it correctly. I did not do that correctly because it says z here when it's supposed to say z1 and z2. And that's interesting. What? Any tips on making music with the PICO-8? Well, the first tip is that the tracker interface is a bit weird. It takes a bit getting used to, but that's like, just persevere with that. And 2, this is something that I guess not everyone actually knows, is that when you're tracking with, you know that you're using like you have SFX slots which you kind of use as patterns. What I've noticed that not everyone knows is that you can use the first 8 sound effects as instruments. You can use this in like samples that other SFXs play, and this is crucial for making good sounding drums, for example. Maybe would it be a good idea next time? Maybe I should Maybe I should, when I stream next, maybe I could make some music. Would anyone be interested in seeing that? Okay, maybe I'll do that next time. Okay, so, but anyway, is it now rotating? Yes, now it's rotating it properly. And now let's do the same for the symmetrical, the other side. So now, yes. So now we have rotating points. What we're gonna do with these is we're going to draw a rectangle. So how did I do this? Okay, fortunately I was testing this same thing earlier, and because I know that I sometimes forget how I do things. Oh yeah, obviously. So we're going to want to calculate the slope, because we're going to draw a rectangle or a 3D rectangle from using scan lines. So for that we need to we still need to flatten our point, and we have no use for the old three-dimensional values at this point. So we're just going to be replacing those with the flattened versions. Okay. This is definitely not an elegant way to do this, but this is a way to do it that's fast to write. So now, let's calculate the slope between those. So that's going to be, how was it? Oh yeah, the difference of the x's divided by the difference of the y's. And we need to also define a direction, so we're going to be assuming that we're going to be incrementing this scanline y value by 1, but if the point y2 is actually, okay, sorry, I'm still cheating. This is actually, I know this is probably not something that I should be doing. I'm calling live coding, but so if if y1 is actually greater than y2, then the direction is going to be -1, and we're going to be defining the scan line that we're going to be drawing. The y is going to be y1 from where we're going to start drawing, and the x is going to be x1, and of course we don't need, for scan y is y1 and y2 and incremented by direction. So line x and scan y, and now we're drawing a symmetrical line, so it can just be 128 minus x scan y, and the color is going to be 15 for now. And now we're gonna increment the x by slope times direction. Now let's see if we have a rotating thing here. No, we don't, because we're missing a do. And we still have we're missing an end. Right. So now we have a spinning thing here. Now what I want to do is map the picture we have in our sprite map into that rectangle. Now we could just map it linearly, but that would lead into texture deformations, because that wouldn't we wouldn't have a good perspective here. So we can't do that linearly, but fortunately, because basically we're going to want to define the u and v values. Those are like the texture coordinates for each pixel. Now we can map the u, which is going to be the x, we can map it just linearly from left to right, because those are just like which one was left to right? Was it horizontal or vertical? Either one of those. It's going to be that kind of line. So that we can do linearly. But we cannot do the v value, which is going to be the y value, like that, because it doesn't interpolate line linearly. Fortunately, this is a thing that we can use, because when we draw a line in space, in screen space, the v value, it doesn't interpolate linearly. However, this value, 1 divided by v, is going to interpolate linearly. So we can use that to get a good perspective. So now let's define the v value, the kind of inverted, whatever the right mathematical term is, values for our vertices. So let's just call them inverted for now. So in v1 equals, so the v value, because we're the reciprocal, yeah, okay, thank you. So yeah, the reciprocal. So because our texture is 128 by 72 pixels, so we're just going to be using those as v values. So the reciprocal of v1 is going to be 1 divided by, did I remember this correctly? Oh yeah. Actually, this is not like I wrote it. So yeah, it's just gonna be 0. Okay. And the I just explained this totally wrong, because this code is not at all what I wrote here. I mean, the reciprocal of z is actually that interpolates really linearly, so we can use that. Rec z1 equals 1 divided by z1, and rec z2 equals 1 divided by z2. Now oh yeah, it's the v value is v divided by z. So we're going to be defining this as 0 divided by z1, but that's obviously just going to be 0. And the value for 2 we're going to be mapping to 72, so that's going to be 72 divided by z2. Yes. And now we can do slopes for these as well. So slope equals, so slope rec z equals the difference between those, and again divided by the difference of y2 and y1. And we can do that with the v values. So now we have slopes for the reciprocal of z and the v. Now we're going to be starting, the v that we're going to be starting at is going to be 0, and v interpolate, let's just go v like this, so it's going to be starting at 0, that's the first v value, and as in the scanline from the sprite map that we're going to be drawing, and then the z that we're going to be starting at is going to be, yes, so like that. So now we have these values which we need to increment every time. So vi is slope rec v times direction, and zi equals is incremented by slope rec z times direction. So because we can calculate the reciprocal of z like this, we can calculate the, is that reciprocal anymore? Okay, well, this math is explained in Wikipedia. You can check it there. So we can use, now we know that the, yes, sorry, this is a bit of a mess again, but I think it's kind of, so we know that the actual z value at this point is going to be 1, it's going to be the reciprocal of the reciprocal of z. So now we know the z value of this particular scanline. We can now define v, which is going to be there, that times the, yeah, that times z. And now that we know the z value, v value, we can actually draw the line from the sprite map. So the coordinates we're reading from the sprite map, the coordinates are going to be x0 and yv. The size of the area from this sprite map we're going to be reading is going to be width 128, height 0, and now where we're going to be where we want to draw this is 6 64. Actually, we're gonna want to. Yeah. So the left corner is gonna be x1, and the y is obviously gonna be scan y, and then the width of the area is gonna be 100. So the other corner is going to be 128 minus x1. So, and we also need to decrement the x1 again, so that it's going to be the width value. So it's going to be 128 minus 2 times x1, I think, and the height is still going to be 1. Did I do this correctly? Let's see. Oh yeah, and if obviously not x1 but x. So, is everything working correctly so far? Everything is not working correctly so far. There's some variable I've misnamed. Oh yes. Now, let's see. And this does not look right at all. So, fortunately I wrote everything this so I can see what I did wrong. So, 1. Well, the one thing that I did differently is that I defined the x value as width, but okay. What am I doing wrong here? Am I miscalculating a slope somewhere? I don't think I am. The z needs to be yes, and the vi needs to be yeah. Those are at least defined correctly. Let me out, what am I missing here? This worked perfectly earlier today. Okay, I'm going to be copying this here so we can go line by line what the issue is. Yes. This is pretty much what it looks like when I'm coding a demo, so just a bunch of time before I realize some elementary mistake that I've done. So V is V linear times Z. Z equals the reciprocal of Zi. And now good thing I made notes, because I would be, if I didn't have notes, I would probably be wondering for an hour what I did wrong here. So that slope is defined correctly. That slope should be defined correctly. that slope should be defined correctly. Yeah. Bizarre. This is very, very bizarre. I could just copy the code all in all from there, but I'm gonna try to figure this out. What am I missing? Help me out. Because I know there's probably someone watching this who's a lot better coder than I am. Okay. Well, one thing I did differently here is I defined that like this, and this shouldn't be it, because this is just related to how I draw the thing. I mean, obviously it's related to how I draw the thing, but this is related to how I define the X location, so what happens now? Okay, yeah, this is pretty much what I expected. And let's use this SSPR here. So we now have our new width value, and which we're going to be using instead of X. Okay. There's some pretty simple mistake here still. I'm just not seeing it. It's not mapping it correctly. I have no idea why not. You know what? I'm gonna cheat. I'm just gonna. Yeah, see you next week. I'm gonna do some music here next week. Okay, so I'm gonna be lazy. I'm just gonna copy my code that I wrote earlier today, and maybe I'm gonna be able to figure out later what the very simple mistake that I made was. And yeah, now I don't have a Z buffer here yet, at least. So we're gonna have to comment that out. And yeah. And of course now I'm missing these. And oh, of course the camera. So now we have a proper texture mapper here, which is actually, I have no idea what's different from the version I made earlier, but obviously there's some issue, because now it works and previously it didn't. So we can also make a box out of this by making a for loop out of this and do this 3 times and increment the theta by I times 0.25 every time. Now we're gonna have a box, but all the faces of the box are still going to be drawn in the wrong order, so let's see what it looks like. Oh, let me see what I do. Oh yeah, and also one issue is that we're going to want to actually make black not transparent. Okay, but yeah, as you can see, it still draws the faces in the wrong order, and this is probably not the best way to do this in this case, but now I can display how a Z buffer works. Now a Z buffer is just a value where a Z buffer is how a modern day renderer would use to solve the visibility problem. So it just stores the depth value of all the pixels that have been rasterized. Now we cannot in PICO-8 doing a full screen Z buffer for every pixel. It would be prohibitively expensive, but we can do a one-dimensional Z buffer for just every scan line, so let's do that. So let's define Z buffer. It is going to be... No, actually we're gonna have to reset it every frame, so let's define it in the draw loop instead. Now Z buffer is that, and now let's fill it from 1 to 128, and every line of the Z in the Z buffer is going to have some. So yeah, this could be done with like backface culling. We don't really have any specific reason to even draw the faces that are looking away from the camera, but we're going to be doing it now, so I can display this Z buffer thing. So yeah, for every scan line, let's have some value. For example, starting value. Is there a built-in Pico 3D rasterizer? No, you have to use basically, you have to use a similar kind of sloping thing that I've used here to rasterize the triangles yourself. So yeah, there's no 3D functions built in PICO-8. So let's just assume that every line on the Z buffer is going to be starting at depth -20. Now we can use this, so it checks the Z. Now if the Z value is greater, if it's closer to the camera than the closest scan line drawn on the draw previously, then it updates it to be Z, and there. So now it should not be drawing a scan line if there is a scan line that's closer to what we were going to draw. Let's see if that works. Do. Well, of course, a do is missing. and of course it's an array, not a integer. And now it works. And now we can also, if we want, now that it is drawing all the lines, we can do, for example, this, so that the rectangles aren't entirely connected. So now it's possible to have them a little bit of, oh yeah, I don't want to be changing the y, of course, so I'm just going to want to change the z both these times. And now, as you can see, we have a kind of like a box that's open at the seams. And yeah, and this is something that we couldn't do if we didn't draw the back faces at all, because then it would just be drawing black in the seams. Now, there's one more thing that we can do now that we have a z buffer. You notice that I had these max z and min z values here. I used them to do this. So let's make a function of this. Function draw box min x min z, and copy all of these here into our new drawBox function. Now we can do this in, so now it basically, every time it draws a line, it also checks if the z is within a certain range, otherwise it doesn't draw it. So we can, for example, do this. Draw box, and the minimum value is gonna be -20, and the maximum value is gonna be -5. And I tend to compare number with nil. Why are you comparing a number with nil when I should be... Why is it not receiving these values? Max? Oh, because I don't want to be, it's not a minx, it's a max z. Yeah. Did I name them correctly? Max z, min z. Yeah. So now, interesting. If z is, oh yeah, these are the wrong order, so now, yes, you can see it only draws, it cuts the box at z value -5, when we can now draw the other half of the box. And now, what's the point? Well, the point is that now we can draw things that go inside the box. So let's move this camera into our draw box function, so it will reset every time. And between these two, for e equals 1 to, let's say, 30, then y equals 48 plus random 32. So now it's going to be, we're going to be drawing something at y of 48 plus a random value of maximum 32. So line 0 y 121y, and let's have it, the color be this. It's a bit hectic. So yes, as you can see, now we have lines that are going inside, moving inside the box. That still kind of doesn't look nice. Let's just have a circle there. Yeah, now we have a ball inside there. Actually, we could do one thing. So for x equals, so x is going to be starting as the modulo of the frame counter and let's say 20, and it's going to end this loop at when f. No, actually, let's make it so that it starts before 0, and the end is going to be, let's say, 148, and the increments are going to be 20. So now oh, sorry, yeah, not the first time, I forgot to do. So yeah, so what I've done here is we have now a for loop where the x starts as the modulo of f and 20. So basically, if f is 21, then that modulo is again 1. Now let's see if that works. Now let's still a little bit, and let's just do something about the radius still. So let's have it be 6 plus 3 times the sine of f times 0.01, for example. So yeah, now we have some balls going inside our box that's splitting at the seams. So yeah, it's unfortunate that I kind of had to copy a lot of this code. I still have no idea what I wrote wrong, but it now works. It now has it displays how SSPR works for texture mapping. It has limitations. You can only use it for basically horizontal or vertical objects, because it can also only draw horizontal or vertical lines. There's a new version of PICO-8 coming out, which can draw lines from the sprite map that are not horizontal or vertical. You could use that for affine texture mapping, which is what the PlayStation 1 uses. Now, unfortunately, that will result in some distortion, because it's a linear mapping. The way this is fixed on the PlayStation 1 is that they use a lot of surface subdividing, because the PlayStation 1 can draw a relatively large amount of triangles. We don't have that luxury on PICO-8, but as soon as the version of PICO-8 with that feature comes out, I'm gonna see if I can do some kind of 3D texture mapping using that. But anyway, this is what I wanted to show this time. Thanks for watching, and see you next week. I'm gonna be doing not doing visuals probably, but I'm gonna be doing music next time. So again, Wednesday at 18:00 Finnish time. And thanks for watching, and have a nice evening.